Hey friends, welcome back to the channel and to the 11th episode of Research Papers Summary. Today I'll be covering another ACR 2020 paper, Embeddings of Label Components for Sequence Labeling, a case study for fine-grained NER tasks. In this paper, they propose to integrate label components information as embeddings into the NER models. They show that NER entity labels can be decomposed into different components, and the sharing of these components between labels are very useful for label predictions. In this video, I'll first cover the context and contribution of this paper. I will then dive straight into the proposed methodology, the embeddings of label components, and lastly, I will finish up this video by sharing some of the experimental results and analysis. I hope you find this video useful. Let's get into it. If you're new here, my name is Ryan. I'm a first-year PhD student based in London, and on this channel I mainly share my personal development journey as a student entrepreneur, covering my PhD research in AI, my entrepreneurship journey, as well as different life design topics. Being the first generation person in my family to pursue higher education and different life and career pathways, I hope that these videos will provide you with useful information, inspiration, and courage to take more actions and live a happier and more intentional life. If you're a student, entrepreneur, first generation students, or all of the above, consider subscribing for more informative videos in the future. Sequence labeling is the task of assigning a label to each word in the sentence. One of the sequence labeling tasks is the NER task, where each word in the sentence follows the BIO tag schema. Traditionally, the sequence labeling models uses the inner product between word representation and label embeddings to compute the probability of labels for each word in the sentence. The problem with that is that the label embeddings are computed independently without considering the shared components across these labels. Yet, most of the labels that we have in the datasets usually contain shared components. This problem motivated the authors to propose a methodology that learns and shares embeddings of label components. The paper uses fine-grained NER as a case study to evaluate the effectiveness of this proposed methodology and also to assess whether this proposed methodology can work well with infrequent labels. Overall, the main contributions of the paper are as follows. Firstly, they propose a method that shares and learns label component embeddings. And secondly, they show that the proposed method can achieve better performance in fine-grained NER than the standard sequence labeling models. The proposed method is also effective with low-frequency labels. Let's now talk about the embeddings of label components. Before introducing the embeddings of label components, let's first take a look at the standard baseline model. Here's the baseline architecture. As you can see here, we have the traditional encoder layer to convert each word into its feature vector. We will then compute the inner product between feature vector and label embeddings and pass the results into a softmax layer to compute the label probability and assign the highest probability label to each word. The one thing that I would like to point out here is that the main contribution of this paper is that they're proposing a new way of computing the label embeddings to take advantage of the shared components. Overall, in sequence labeling, for each word in the input sentence, our model will output the label with the highest probability. Now let's take a look at how we can integrate label component information as embeddings on top of this baseline model. There are two steps. Firstly, we have the label decomposition. Here, we simply decompose each label into its components. Depending on the labels, each label consists of multiple types of components. For example, B park will be decomposed into B for the beginning of the entity and park for the type of the entity. The second step is the computation of label embeddings. Once we have the components of each label, we can then assign an embedding to each label component and combine the component embeddings within a label into one single label embedding. Here, the paper experimented with two common techniques: the summation of the component embeddings and the concatenation of the component embeddings. The one disadvantage of the concatenation method is memory efficiency. As the number of the label components increase, the dimension of the label embeddings also increases. This label embedding computation allows models to share embeddings of label components that are commonly shared across labels, and it also allows us to capture the hierarchy labels. In terms of the datasets in this paper, we have the extended name entity corpus for English and Japanese fine-grained NER. We also categorize each label into three different classes: low, medium, and high frequency, so that we can investigate whether our proposed method is effective for low frequency labels. In terms of the model setup, we use BERT as our encoder. Our baseline model uses label embedding matrix without label components, whereas our proposed model uses label components to construct the label embedding matrix. The one thing that I want to make very clear here is that the only difference between the baseline model and our proposed method is the way we construct the label embedding matrix. And so what this means is that any performance difference between the two models will be caused by the label embedding matrix. Overall, our proposed methods with summation and concatenation both outperform the baseline model in both the English and Japanese datasets, showcasing the effectiveness of our proposed method in constructing the label embedding matrix. The second finding is that for all the label frequency clusters, our proposed model with summation scored the best results. In particular, our proposed model with summation has the largest improvement in F1 scores against the baseline model in the lower frequency labels. This showcased how exploiting label component embeddings can improve the generalization performance of the model. One thing that I would like to point out here is that the entities in our dataset has a hierarchical structure. What this means is that the label components at higher layers tend to appear more frequently than the ones at the lower layers. Because we're showing components between labels, here we can expect high frequency label components to help the model predict low frequency component labels. Let's take a look at our results for this hypothesis. Here you can see that the proposed model with summation was able to outperform the baseline model, showcasing its ability to predict low frequency labels using shared components. However, our proposed model with concatenation wasn't able to outperform the baseline model. We believe that this is because the concatenation of label component embeddings give our model less information. Lastly, I want to finish up this video by showing the visualization of the embedding space between the baseline model and the proposed method. As you can see here, the label embeddings learned through our proposed method form clusters as they share label components. With the baseline method, no distinct cluster was formed. Additionally, we found two findings with our proposed method. Firstly, two distinct clusters were formed, which relates to the two span labels, the B and I labels of the BIO scheme. Secondly, labels that have the same top layer label also form smaller clusters within the B and I label clusters. This is shown in the enlarged view of a cluster in figure 3C. And that's it for today's video. If you like this video, be sure to subscribe as I'll be covering more research paper summary in future videos. In the meantime, feel free to check out other videos on my channel. Thank you for watching. I'll see you guys around next time.